All right, so in previous lectures, we talked about motion essentially along the line where all the forces either sum to zero or maybe they are unbalanced, so there's an acceleration. But essentially, whatever direction that unbalanced force is the direction of motion we're going to have. So let's expand this into multiple dimensions, like circular motion, where we have sort of an x component and a y component that's always changing. So we can't just look at linear motion like on the line anymore. All right. So as far as forces in two dimensions, Newton's laws of motion, they describe all motion, okay, not just straight line motion. So that is important to remember that these laws will work in pretty much any situation that is an inertial reference frame. And we're not limited to just like one-dimensional motion. So Newton's second law can be applied to two-dimensional motion as well. Essentially, each direction can have their own acceleration. So remember that Newton's second law essentially just says F equals ma, right? The sum of the forces. So if we add up all the forces, there's an imbalance, then we have an acceleration. So the idea is essentially we can break it down to all the forces components in the x direction, and then all the force components in the y direction, and then these are going to be causing separate independent accelerations in these directions. So if the x and y components of the acceleration are independent, then this is valid. So that is very important. And I'll show an example shortly where it's the case that they're not independent. But as long as your one acceleration value doesn't influence the other, Newton's laws hold. Okay, so let's look at this quick example here. So we have a small rocket for gathering weather data, has a mass of 30 kilograms and generates 1.5 kilonewtons of thrust. On a windy day, the wind exerts a 20 Newton horizontal force on the rocket. Okay, so let's see. Let's think about what we have. We have a thrust, so that's going to be vertical. And then we also have a horizontal force. Okay, so it sounds like this horizontal force is essentially going to be independent. So if the rocket is launched straight up, what's the shape of its trajectory? Okay, now normally we'd think it's straight up, straight down, right? But we do have a force coming into the side. So it's not exactly parabolic motion, because that's when you launch at an angle. It's just this vertical motion, but then we also have a completely independent horizontal piece as well. All right, yeah, it's been launched vertically upward, but there's wind. So by how much has it been deflected sideways when it reaches a height of 1 kilometer? So we want to know essentially what its overall trajectory looks like and how much has been deflected from the origin at 1 kilometer. Okay, and then there's just a little extra note here, just because the rocket goes much higher than this, assume that essentially the mass is the same. So we are burning fuel quickly, so we're just going to assume that it's negligible for now. Okay, so as always, we need to come up with a picture. So here's my pictorial representation. So notice we got some deflection going on. We also have the vertical thrust. And the question is, the first part is, let me see if I can highlight it. Maybe, let's see. Yeah, so what is the shape of its trajectory? That's one piece. The other piece is how much has it been deflected? So essentially what we're wanting to know is what does its path look like as it gets up to its upper altitude? So we want to know its height position, its height coordinate as a function of its x coordinate. And we also want to know its deflection. So just how far over is this? What is x final? So after we draw out our diagram, we can list our knowns and unknowns. You'll see here that we've identified that we do want to find x final. And then the last thing is we just want to draw a free body diagram. So we know we have a lot of thrust up, so big vector upwards, and then some gravity downwards. And then we also have this drag force from the wind. We won't worry about like a formula for drag. It's given to us here. We just know that it's 20 newtons to the right, essentially. Okay, so that's all set up. We know what the physics is. The rest is just summing the forces, algebra. All right, so as usual, we will add up all the forces. It's just those three from our free body diagram. Thrust up, gravity down, and drag to the side. Now, clearly these are unbalanced. So instead of equaling 0, these are going to equal ma. We have unbalanced forces, so we've got some motion going on here. So let's think about the x direction. When the x direction is just our drag. That's the only thing, so that was easy. We know that equals max because we're talking about the x direction. Let's see if I can zoom in here a little bit. Okay. Next we have, well, we can solve for acceleration. That's just the drag divided by m. I mean, that's super easy, no big deal. The next part is the y direction. So in the y direction, we have the difference between these two forces. We have thrust upwards trying to propel the rocket, and we also have gravity fighting against that. That also has to equal ma, but the acceleration in the y direction could be different than the x direction. So that's why we have a sub y here. Now, when we solve for our acceleration in the y direction, you'll notice that the formula is a wee bit different. We have more forces, that's why it looks more complicated. So essentially, it's just the difference, this difference divided by the mass. Okay, then, well, we know what the weight is, so we can go ahead and plug in that mg, and it's negative because it's force due to gravity downward, right? Now, we have our acceleration in the x direction and the y direction. What we can do now is plug that into our regular old kinematic equations, and then that'll tell us where our x position is over time and where our y position is over time. So this is going back a few chapters in the textbook. We're going to think about how to use these 2D kinematics equations again. So with the x direction, you'll remember this should be familiar. So it's got our initial position plus an initial velocity times time, and then our acceleration component. Well, we know from our original setup that this thing starts at the origin. So the initial position 0, we know that it starts from rest because the rocket was sitting on the launch pad. So these terms I've highlighted in orange are actually 0. All right, and the only thing left over is just our usual 1/2 at squared. Now remember, this is our x direction, and we have our x component of acceleration, right? So we can actually go back and grab that. It's just d over m. Okay, we can plug that in. And it turns out the equation for our x kinematic piece is simply, let me get rid of that, is simply just d over 2m times delta t squared. Oops. There we go. Okay, so we can do the same thing in the y direction. Well, we know that the y components of position and velocity, those initial pieces are 0. So the only piece left over, same thing as in the x direction, it's just we have to include our y component. So here's our acceleration in the y direction. We calculated that earlier, so we can plug that right in. It looks a little messy, but we're dealing with acceleration from unbalanced forces, so it's going to be a little complicated. Okay, and then after doing that, this is the component of our y direction. So we have our x coordinate as a function of time in the previous line here. And we have our y coordinate as a function of time. Now you remember, if we have x versus x as a function of time, y as a function of time, we can put these together and make a parametric equation, which is just those pieces in i hat j hat notation. So at any given time, you can plug in your time in seconds here. If you want to know where the rocket is at, I don't know, 12 seconds, you can plug it into this big parametric equation, and it will give you the xy coordinates of where it is in your coordinate system. Okay, Now, what about its trajectory? We know what these coordinates are as a function of time. So now we need to think about what this plotted out is going to look like. So if we're watching it in our coordinate system, where is it actually physically going to be? Not just x versus time or y versus time. Okay, so now we need to think about its trajectory. So both its x and y components demonstrate acceleration. Okay, remember both of those terms have t squared. So that means the plot of these are going to have some sort of like parabolic shape to it. Okay, we've got an acceleration in the x direction and the y direction. But we want to know what that looks like when we put those coordinates together, because you'll remember from a previous lab that just because your x and y coordinates have this acceleration term in them, the actual overall trajectory may not look like that at all. Okay, so even though we have x of t and y of t, we want y of x. Okay, so let's actually combine x and y, okay, such that we can build y of x. And all we have to do is just take x of t and put it inside y. That's all that's going to happen. We've done this before. Okay, so here we have x of t. Now what we can do, we can be really slick about this and just solve it for delta t squared. Okay, now when we do that, we get this piece right here, 2mx over d. Okay, that equals delta t squared. I just moved the 2m over and the d over. That's all that happened to get delta t squared by itself. All right, so now we need to take this, our x statement, and put it into y. Okay, so here's our original y statement from the previous slide. We built that from the free body diagram. So what's going to happen is we're going to take that delta t squared, and we're just going to replace it with that x calculation from the line right above. Okay. So this, since it equals delta t squared, is going to get replaced. Now we can do a little simplification. There's a mass that cancels out. There's a 2 that cancels out. And this is what we're left with. Okay. Now, if you think about this, what this is saying is just y of x equals F thrust, I'm going to abbreviate with just a T, minus mg over d times x, okay? Now, this is just a straight line. This whole term in here, that term is just m. This is just y equals mx. So even though we have an acceleration in the x direction and an acceleration in the y direction, what you're looking at when we actually watch the trajectory of this rocket is it's actually just following a straight line, y equals mx from the origin. Now it's going to travel that line faster and faster because its coordinates are accelerating. But when we watch this happen in real life, it's just going to travel a linear distance. It's really interesting that some of these really complex kinematic equations, when you look at the actual trajectories, they can be quite simple. Yeah, so that's what this yellow point here is just although the individual components are quadratic, the trajectory appears as just a diagonal line upward to the right. Now the question also asks about some deflection. So what we can do is actually just flip the equation, solve for x instead of solve for y. And when we do that, we get this statement here, okay? And that really just tells us at some height y, how far away are we from the origin. So we can plug in our values and it turns out it's about 17 meters away from the origin. So after 1 kilometer of vertical distance, the wind has pushed the rocket 17 meters to the right. So that was just a quick example showing that we can bus up accelerations into the x direction and the y direction. However, one word of caution. So not all accelerations have independent components. Okay, this should be components with an S. So essentially, consider the simplified drag model, where we just said drag equals 1/4 AV squared. Now, if we take a projectile motion problem, maybe something's being launched this way. Now, remember, drag always opposes the motion. So drag is going to be this way. And it also depends on the value of V. Now, think about this. So we have Velocity for a projectile motion problem pointing up and to the right, drag is going to be pointing down and to the left to counteract it. Now, if we try to come up with the x and y components of drag, we could maybe try and write it like this. So the x component would be the cosine piece of drag and be negative because it's opposing the direction. The y component, we could, sine theta because sine gives us the y component generally. The issue here is even though we try to pull these apart, look at what's in the formula. V, total V is in there. Remember how the main vector V, so I'm going to move over here to my plot here. Remember how this main vector V is always Vx squared plus Vy squared. So no matter what, no matter if we try to break up dx and dy, because total V, the main vector V, is in the equation, we're always going to have x and y sort of collapsed in there. So even here, this is Vx squared plus Vy squared, because that's the magnitude of the vector. And even here, same thing again. So we literally can't completely separate this drag equation into its x and y components. So just be aware of situations like this where the velocity is still a part of both equations and you can't completely disaggregate the two. All right, so to move on to circular motion, we actually need a new coordinate system, because you can imagine trying to talk about like x and y coordinates on something that's spinning, like a CD or a disk or something. So let's think about a new way to set up these problems. So we have a Cartesian grid, which is not the best. Let's move on to maybe this thing here, which is just an RTZ coordinate system. So let's just get rid of the Cartesian grid completely. This is going away. And let's think about a coordinate system that actually rides along with a particle. Okay, so you can see my particle over here in this first image. Got a particle here, and then at some later time, it's over here. I'm going to switch back to a more bold color. Okay, now, so for this particle, we have three axes, just like a XYZ axis. So we have the R axis, okay? So the R axis, that's actually going to point inward toward the circle. So we have that here, here. So there's our R axis. We have the T axis, which is tangent. Okay, so we have this axis, which is tangent to the circle. And we have the Z axis. Now the Z axis is essentially our elevation above the circle. Okay, and it's always perpendicular to the plane of motion. So it's essentially your elevation. For any vector in this new coordinate system, as you can see over here, we have this big vector A. We've got a new angle. We have this phi. Okay, so phi is essentially the angle depending on, okay, if your vector starts pointing toward the origin, your phi angle's 0. And as you start pointing into the circle, but not at the origin or not at the center, right? So here you can see you've got this piece, this a little bit of deflection. That's what phi is going to measure. So phi is measuring your inward point, but how far from the center of the circle it's pointing, or at what angle from the center of the circle is pointing. And of course, we can get components of this A vector if we wanted to. We just base it off of phi instead of like theta, like we're used to doing. So I know this is confusing. This will actually be simplified in the problems we do here in a few minutes. So just remember that essentially we're just going to identify a new coordinate system and let it ride along with the particle in circular motion. All right. So the velocity vector in circular motion is tangent. Oh, I should note this is for uniform circular motion. So the particle is not speeding up, not slowing down. Same speed around the circle. That's not changing. Okay, so in this situation, the velocity vector is tangent. Okay, you can see that over here. Our velocity vector is tangent. That's on the t-axis, so that means anything not tangent, any velocity component is 0. So we're not getting closer to the center of the circle. We're not getting farther away, so our radial velocity is 0. We're not moving up and down, so our z velocity is 0. The only velocity we have is the one tangent to the circle. And you'll remember from several lectures ago, that's just the change in arc length over change in time. And we can rewrite that as essentially r omega, where omega is the angular velocity. Okay, so hopefully this is a review. So the acceleration of uniform motion, the only acceleration where there is an acceleration is that the piece that's holding you in the circle, because you could have a tangential acceleration in non-uniform circular motion, but in this case, the only acceleration present is the one that's going to keep the object moving around that center of the circle. Okay, well, we know that this is just VR, or v squared over r, and we can rewrite that. We can take this velocity, move it down here, and plug it in, and we just get r omega squared. And since there's no other accelerations going on, these other accelerations just equal 0. Okay, so what about forces? We know how to talk about velocity and acceleration in uniform circular motion, but because we do have this constant acceleration, we can actually talk about forces. Newton's laws actually hold up. So Newton's law, Newton's second law, F equals ma, still works. We know that we have an acceleration, but this time it's a centripetal acceleration. So Newton's law we can extend and just change it to ma sub c. So a sub c equals centripetal acceleration. All right, so let's see. We've got a particle of mass m moving at constant speed v, right? Okay, because this is uniform circular motion, around a circle of radius r, which means for this to happen, for this particle of mass m at speed v, the only thing or a particle moving around the circle. Let's think about what if we take that circle, and we turn it up this way, okay? So turns out that motion in a vertical circle is not uniform circular motion. So to demonstrate this, we're going to look at this roller coaster car over here on the right. So in this case, as the car goes up, let me draw it. Let me switch colors and draw it. There we go. So in this case, as the car goes up, okay, it's actually going to slow down. The car slows down as it goes up. Okay, you can imagine because it's got gravity fighting against it as it goes up. And then when it completes the loop and starts going down the other side, it'll actually speed up as it comes back down. So that's over here on the other side. So only, this is interesting, only at the top and the bottom of the loop is the car's tangential acceleration 0. Okay, so only up here, we only have a centripetal acceleration, and in the bottom we only have pure centripetal acceleration. Obviously we have some around the circle, but these are the only 2 points where it's just pure centripetal acceleration, no other tangential stuff. So that means we can actually apply Newton's second law at these 2 points, and only these 2 points. So at these 2 points, the only 2 forces we have are essentially gravity and the normal force. So at the bottom of the loop, let's look at this first. At the bottom of the loop, the normal force is responsible for holding the car in the circular trajectory. So the fact that the track is curved as the particle wants to move in a straight line. If this track were to just go away, the particle would just take off in a straight line, or the car would just go in a straight line. So what's going on here is because we have this curved surface, we get some extra normal force from that. That's what's pushing us, always changing our velocity. So the normal force is responsible for holding the car in the circular trajectory, right? And that's why if you look at this graph over here of our free body diagram, see how tall the normal force is, how tall the vector or how long the vector is. We're getting this extra normal force from the curvature of the track. And then that extra normal force is going to help keep us in the circle. Now at the top of the circle, the normal force and gravity are actually holding us in circular motion. See here at the bottom, the normal force is holding so the normal force is the MVP keeping that cart in the circle. At the top, both the normal force pointing down and gravity are what's causing the circular motion. So up top, this normal force actually gets an assist. Now let's actually sum up these vectors. So let's look at the bottom of the loop first. So we're going to start with Newton's second law in circular motion. Okay, so we have the forces summed up equal ma. Clearly there's a centripetal acceleration, the forces are unbalanced. Well, since we're looking at circular motion, we get to replace a with our centripetal acceleration. So all this stuff right here, that's still Newton's second law. Okay, that's still a definition. We actually haven't added up those forces yet. We just know they have to equal mv squared over r. Now let's sum these up. So obviously at the bottom we have 2. We have the normal force and we have gravity. Gravity's negative, it's pointing down. So we need to include that when we add it in. So plus F sub g, we know it has to be negative because of the physics of the situation. So it turns out at the bottom, we just have it turns out at the bottom, we have the difference between the 2 forces, N minus mg. Now, I had to think a minute because I was getting ready to say the difference between the 2 forces, but if we solve for the normal force, okay? If we say, okay, we want to know what N is, we can move mg over, and it turns out the normal force, and we sometimes talk about weight, like the weight of a person is just essentially how much normal force they're feeling, because normally your weight's canceled out by your normal force. But look at what's happening here. We have this car's weight, or maybe the person inside. We essentially have the weight plus extra. So it turns out this is why you actually feel heavy, or you get pushed down into a seat on a roller coaster when you're at the bottom of a loop and then you're gonna head upwards again. At the bottom of the loop, you feel your heaviest because you have your weight plus this centripetal force going on. Okay, and that's actually the reason you're pushed down into your seat. Now, at the top of the loop, we can do the same thing again. Oops, we need to write this as top, not bottom. There we go. So at the top of the loop, what we're seeing when we sum the forces, okay, same thing again. we can solve for the normal force because we want to think about the weight that someone might be experiencing. Turns out it's the difference between the two. Okay, so instead of adding your weight plus centripetal force, we have the difference between those two, and that's going to be less than what we feel at the top. Okay, you can write it out and do the math, but when you have, A plus B, you get a value, but when you find the difference, A minus B, it's going to be smaller. So here you're at the top, you're going to feel lighter because you're essentially feeling the difference between the normal force and your weight. So that's why a rider weighs more at the bottom than at the top. Got to get rid of that T there. All right. So now the question is, we can see from this example that the force of gravity and the normal force help hold a car in a circular path. But here's the key question. So what happens when we lose our assistance from the track? Remember, the track is causing the normal force. Newton's third law, action, reaction. We're pushing against the track pushes back with the normal force. So if we lose our assistance from the track, that means we may be touching it, but we're not like pushing against it. So there's that one instance you can imagine if something starts falling off this track at the top of the loop, you may have been pushing against it. It gets to a point where it's right beside of it, but it loses that push. Now that happens when the normal force equals 0, okay? When the normal force is 0, there's no more contact force. Now, if we go back to a previous equation and say, well, the normal force equals 0, for example, at the top here, if we just say this equation equals 0, we find that the centripetal acceleration will equal, or the centripetal force will just equal your weight, your gravity. So in this one instance, where we're not getting an assist from the track anymore, only gravity is at the top of the loop holding this car in the circle. Okay? So any speed slower than whatever, so right now we're looking at this, V top, whatever the speed is to make these equal, any speed slower will cause the car to just leave the track. Okay, and you can see that over here. So here we have, so if V is greater than VC, so this is our critical speed, essentially. So what is that magic speed that we can make sure, as long as we're at it or above it, we stay on the track? If our actual speed's greater than that, no problem. We can hang out, go as fast as we want to. If our speed is exactly that critical speed, well, that's when just gravity holds us in the circle. That's when we lose the normal force completely. And then if our speed is less than the critical speed, you can see here in the picture, we just leave the track. We fall off completely. All right, now what we can do is essentially just solve for V top. Okay, since they're set equal, we can do that. We don't even need a reason. And we can actually determine how to calculate this critical speed. Okay, and it's actually really easy. It's just the square root of R times G. So the important thing here is just knowing that anything slower cannot sustain the loop. And what's really interesting is there's no mass in this equation. The only thing that determines your critical speed, assuming you're on Earth, is just the radius of the circle. It doesn't matter if we're talking about a little ball bearing or an entire school bus. The speed you need to hit this circle at and get up to the top with does not care about what the mass of the object is. And that to me is a little weird, but it's physics. So now I want to briefly talk about setting up some circular motion problems. I'm not going to walk through these and like plug in numbers and everything. I just want to say, okay, hey, here's a problem. Here's what the free body diagram looks like. And let's carefully sum the forces in the R direction and the Z direction, because the rest is just algebra. Okay, and this isn't a math class. This is where we need to really focus on the physics and make sure we get our equations set up correctly. If you can do that, that's most of the battle. The rest is just algebra. All right, so let me zoom in real quick. All right, so for the first one, turning the corner number 1. What is the maximum speed with which a 1.5, oh, no, I don't want to say that, with a 1,500 kilogram car can make a left turn around a curve of radius 50 meters on a level road without sliding, okay? So it's just a car with a weight going around a left turn. This turn's obviously going to have a radius. So how fast can it do this without sliding? All right, well, we can look at our pictorial representation. So I've got everything labeled here. I've got my knowns, my unknowns. There's not a lot to know. Looks like we just have, I'm trying to figure out where we got our static friction from. So it may be given in the textbook. There's a big table. A lot of these questions don't actually present it. They just grab it from the table, but in the problem set, you'll get it from me. So let's see, looks like we have everything. We've got a little note here. It just says essentially the static friction. So the tire doesn't want to, just take off out of the curve. It's got some sort of static frictional force holding it in. And that's what's causing the circular motion. So here, and this is important, circular motion. The centripetal force isn't just some force out there like gravity or friction. The centripetal force has to be caused by something. So here, the centripetal force holding us in the circle is actually caused by friction. You can see it here on the free body diagram. It's actually pointing toward the circle, toward the center. So some other things to note from this problem as we're looking at the pictorial representation and translating that to the free body diagram. The car is not flying up off the road or sinking into it. So we know that the normal force and the gravity, the gravitational force, those have to be canceling each other out. So we can make note of that here. These have to equal each other. So the only unbalanced force points inward, just as we expect. All right, now when we add this up, we can add up everything in the radial direction. Well, that's just our friction. That's the only force, and we know that force has to equal mv squared. And then in the y direction, or the z direction, sorry, the up-down direction, we have just the difference between the normal force and our weight. We know that equals 0 because the car is not moving up or down. So we could simplify this to just say, like normal, no weird ramps or anything, the normal force is just equal to the weight of the object. All right. So in this one, so a highway curve of radius 70 meters is banked at an angle of 15 degrees. At what speed can the car take this curve without assistance from friction? Okay, so we're going to jet down this curve, and since the curve is banked, that's gonna help us stay inside the curve. So we're not getting. Actually, let me zoom in. This will be good. Okay, so let's look at our pictorial representation. We got the car going around a curve of radius r. We only know the radius and the angle. Not a lot going on in this problem. But what's really interesting is if we add up stuff in the radial direction, remember we have to have a thing. We have to have a force holding us in the curve. So what is our centripetal force? And if you look here and think about it for a minute, it actually turns out it's a piece of the normal force. Remember, since we're on this incline, our normal force is like all wonky. It's got an R piece, it's got a Z piece. That's not the case with gravity. Gravity is just pointing down. It does nothing to help us stay in the curve. But the real MVP here is that one component, that one R component of the normal force. And when you sum up our forces, that you see that. So the only piece is that opposite of the angle, so sine, that one component of the normal force is causing all of our centripetal acceleration. So we're no pun intended, we're banking on this banked road to actually keep us and hold us in this curved path. Now, something else we can do is we can look in the z direction, the up-down direction, and since these things equal each other, we can actually get a value for the normal force. We can actually solve for n, and we see that just doing some quick algebra, it's just n equals mg over cosine theta. So if we wanted to do some more math or figure out an actual value, we can take the stuff we know from the z direction and put it into the r direction. Just like x and y with the kinematic equations, and we can plug in stuff from one into the other. It's the same concept here. Okay, so the exact velocity at which friction is not needed is v naught. Okay, so we can calculate that. It's written right here, v naught. Notice that at that speed, we don't even need friction in the free body diagram. It's not doing anything. Any speed faster or slower, this car will either slide down or slide out of the curve, which means we need to add friction if we want to go through this curve maybe at a range of velocities. Okay, so if v is greater than this magic speed, because no one ever drives at that magic speed around curves where they don't need friction at all to make it around the curve, we need some friction to keep us from crashing. So if we're going faster than that magic speed, the car is going to want to fly out of the curve. So I'm going to draw in, how do I want to do this? Let's see. I'm going to draw in, I'll do a little purple here. So this purple is, if we're going faster than the magic speed, the car wants to slip up because we're going too fast, which means friction has to oppose that motion, right? That's why it's pointing down the ramp. Now, on the other side, if we're going slower than the magic speed, okay, well, if we're going too slow, you can imagine we're going to start sliding down this ramp this direction. Well, friction always opposes motion, so the friction would point up the hill. So that's just the frictional force on these ramps. It's just one extra vector we have to add in. There's really not a whole lot to it. I'm going to do one quick example just to show you how you can put all this together. Uh-oh. Here we go. All right. So a curved ramp of an interchange is built such that it's sloped 10 degrees into the turn with a radius of 60 meters. So maybe this is like a cloverleaf exchange. Given that the coefficient of static friction of a typical car tire is 0.7 under normal conditions, what is the maximum speed a 2,000 kilogram car can travel around this turn? All right, so we're going around this turn. You know what, before I explain it, let's just look at a picture. It maybe is a little grainy, I apologize. So essentially, we got this car going around a turn. We know what the angle is, we know what the radius of the turn is, and we know all the forces acting on it. Okay, so we know we've got we know that we're going fast, so we have friction that's going to try and hold us in this turn. That's what we want to happen. So that means the potential motion of this car is going to be up the ramp, but the frictional force is pointing back down, opposing the motion, trying to keep us in the circle. Okay, so we have this frictional force. Okay, well, we also have the normal force, as always, and it's going to be pointing upward. We also have gravity pointing downward. All right. So those are our three forces, and we can actually start talking about how to break these up. All right, so in the radial direction, so pointing toward the circle, we have the normal force, but we don't have all of the normal force, right? We have, let's see. Let me get in here. So here we have this piece up here, because the normal force, remember, it's wonky. It points in the x direction and the y direction. So only this opposite of the angle, the n times sine theta, that's just the component pointing toward the center of the circle. Okay. Now we also have another component of the friction, right? Because you'll notice here that friction. Let me switch to red. You'll notice that friction isn't pointing directly into the circle. It's pointing down a little bit. So we need, let's see, I'm going to draw it over here. We need this little piece of friction, right? Because we've got two wonky pieces. That's the adjacent piece of my friction vector pointing in R. Okay, so this is pointing inside, but it's just that one piece. Now we know these two forces is what's holding us into the circle or into the curve. So that has to equal mv squared over r. Now we can also do the z direction. So essentially we have the other component of the normal force, okay? So going back up here to our diagram, we have the other component of the normal force, the upper piece. Well, that's adjacent to the angle, so that's going to be a cosine. Okay, that's the piece pointing up. We also have a piece pointing down, right? You'll notice over here on the diagram, there's a piece of our friction that points downward, right? Because the radial piece is this way, friction's pointing down. Okay, so we need to include that little negative chunk there. So it's going to be that component of the friction. It's the opposite piece right here. This is what we're after. That's pointing down, so it's going to be negative. And we have all of gravity just pointing down. So that's the easy one. Okay, now this car isn't like moving up or moving down off the ramp, or off the curved circle, so we know it's going to equal 0. All that's in equilibrium. Now, v is needed. The velocity is needed up here. You mark that. Oop, nope, let me do it in something better. Velocity is needed, but we don't know what n is, right? We have an n here, we have an n here. We need to solve for n, plug it into r, and then we can solve for velocity, okay? So we can totally do that from the z direction, okay, so where everything's in equilibrium. I can solve for n. It's really easy, just some algebra, okay? Now I have an expression for my normal force. The normal force clearly is not just mg, right? We've got more stuff going on, so there's more terms. There's my normal force. So from my radial direction, well, I can isolate n. I can get that by itself. So we still have this normal force from the z direction. We also have this normal force from the radial direction. Now, since we know what the normal force is, at least symbolically, we can combine them. So all I want to do is take this, and I'm going to plug it in to r. Okay, now when I do that, I can do some simplifying. The mass cancels out. There's a gravity that's left over, but this is what I'm left with. Now we're almost there. I just need to move the radius over, multiply both sides by r, and then take the square root of both sides, and that gives me this really gross expression for velocity. The cool thing is we can keep this with us and use it over and over and over. Anytime when we have this setup, but even with different numbers, we can just dump in new numbers and keep finding the max speed for any car as it travels around the curve. So in this case, when we plug in numbers, and I'll leave that up to you guys, when we plug it in and simplify, it turns out we get the maximum speed is about 24 meters per second, and this is roughly about 55, 56 miles per hour, I think. So that seems about right. Taking one of these interchanges much faster than that, going at like 60, I don't think you could do even with really good tires. So that's just a quick setup of a few different radial motion problems, circular motion problems with forces. And as always, let me know if you have any questions, and I will try my best to help you out.